Welcome to Applied Data Analysis in Python. This is a course which follows on from our Introduction to Data Analysis in Python course. That previous course introduced the basic tools that Python provides through pandas to read in data, query data, and interact and select subsets of your data, and finally plot any information you've extracted. The purpose of this course is to take the next step and discover some more advanced tools you can use to start from data and extract information from it. More complex queries than simply, I want to get all the rows that match this label, but more advanced, intricate data analysis tasks. We could name this course Machine Learning in Python, since that's effectively what we're going to be covering. But machine learning is such an overloaded term that I think thinking about what you're doing to your data to get your questions answered, rather than necessarily the umbrella of the tools that you're using, is sometimes a slightly better way to think about how you're doing things. So I'm going to start by moving to the next page in the notes. So, as I said, we're mostly going to be learning about machine learning techniques today, or at least some things which fall under the umbrella of machine learning. Now, machine learning is a slightly overloaded term. I'm going to try to, throughout the course today, explain what machine learning is, how it fits in the context of wider topics such as AI, and how some of the techniques specifically we're using can be used, and why machine learning is more appropriate description for them than just statistics. Machine learning covers a whole host of tools. You might have heard of neural networks and deep learning and things like that. Those are techniques which use machine learning to discover information about data. At the very other end of the scale, perhaps the simplest form of machine learning that I can think of is the linear fit or linear regression. So that is just taking an x and a y axis, a scatter plot, and plotting a line of best fit through your data. That is going to use machine learning techniques when you do it on a computer in order to get the information. And that really gets to the crux of what machine learning means. It is simply a statistical technique you apply to your data, but because you're doing it on a computer, you are using a machine. And so the machine is the thing that is doing the learning, rather than you sitting there with a pencil and paper and doing it by hand. So we're going to start off by launching into doing some data. So I'm going to do a little example here, and I'll pause every now and again to let you follow along and catch up. Otherwise, if you feel happy to, feel free to type as I talk. Almost everything I type is going to be coming out of the pages of the notes. So we're going to start by loading up pandas. So from pandas import read CSV, because we are going to be downloading a file. I'm going to copy and paste this because no one wants to watch me type out a big long URL. We are loading a CSV file. It's downloaded it. Let's have a little look at the top of that file. It is a CSV file, which if you had a look at it, you'd see it's 2 columns of text separated by commas. Therefore, it's been read into pandas as a data frame, which is a table which has 2 columns. The first column is labeled X, the second column is labeled Y. We also have a row index for each of the rows. Largely, we're going to be ignoring row indices in the data today. We are just going to be selecting columns from our tables of data. This table, as I said, has got 2 columns, X and Y. And I'm going to start by trying to clarify some terminology, because the sooner you get the terminology understood, the more easily you're going to pick up more advanced terminologies and concepts as we go through. And so the first thing I want to point out is the use of X and Y in machine learning. They have the same meaning as your traditional X and Y on your scatter plot, where X goes along the bottom axis and Y goes on the upwards axis. They're usually drawn that way because X are your independent variables, the things you've measured, and Y is your dependent variable, the thing that you are trying to find out about. And the same thing happens when you're doing stuff in machine learning. It is usually the case that you collect your X data and you want to use X to predict what Y is going to be. In this table here, we have one single column of X. Though it's possible, and we'll see this in the course today, you can have as many columns of X as you want, X1, X2, X3, etc. It's usual that you only have one column Y, though in principle it's possible to have more complex data there. So at its root, what we're going to be doing with machine learning today is using X to predict what Y is. And that's exactly what we're going to do with our scatter plot here. But let's have a little look at what our data looks like. So first thing to find out is how many pieces of data we have. It's telling us the X and the Y columns both have 50 rows in. So we've got 50 data points. Once you've got a vague sense of the shape of your data, the very next thing I tend to do, and we'll be seeing more and more in this course why that's a useful thing to have, is I'm going to look at what the data looks like when plotted. So let's do data.plot.scatter X and Y. And we get here a scatter plot. You see our data is looking relatively linear, starting in the bottom left, going up the top right, but there's a bit of scatter to it. What we want to do is, for a given value of X, predict more or less what the value of Y is. This is what a linear fit does. So I'll just give you 20 seconds or so to copy those lines of code into your notebooks, check you get a plot that looks the same as what I'm seeing, and then we can step on and start actually using some machine learning on this data. So hopefully that's all working for you. You've managed to load in the data, get the scatter plot going. So as with all data analysis tasks, we've started with our data. We've looked at the shape of it, we've looked at how it looks when plotted. We've guessed what the approximate relationship between the parameters are. We've guessed that between X and Y there's going to be a linear relationship of some kind. Once you've decided how you want to represent the relationship between your X and the Y, the next thing is to go and find some piece of code which is actually going to be able to extract the underlying parameters of that relationship for you without having to do a whole load of maths by yourself, by hand. In the course today, we're going to be using a package called scikit-learn. There's also another package called stats models. Both of these are linked in the notes. So if you have more complicated statistical things you want to look at, then stats models might be a place to look. But for most machine learning tasks, scikit-learn is going to give you a nice, easy to use interface to extract most of the information that you need. So let's start by extracting our model we want to use. So we're going to go from sklearn. Now we are looking at linear models here because we think there's a linear relationship between the two of them. So there is a linear model package inside the scikit-learn package, and from there, and I found this out by Googling and looking at the documentation, there is a package called linear regression. So every model that scikit-learn implements is implemented as a class. You import the class that you want to use, you then make an instance of that class. Now at the point you make an instance of that class, it's effectively making an empty model which knows how to learn from your data, but hasn't yet learnt anything from your data. So we do something like linear regression. Linear regression is a class, and so we can call it with a pair of brackets like a constructor, and we assign that to a variable. This model object is now our model, which is ready to learn from our data, but is currently got random or empty attributes inside it. When we show our data to this model, it is going to go away and tune the various parameters that describe how the relationship works. In the case of a linear regression, the two parameters that are going to be tuned are going to be the gradient and the y-intercept in principle. More complicated models will have more parameters inside them that are going to be learnt as the model looks at your data. There are also things that you can tune on a model which you set once up front, which aren't learnt from the data, but you as a data scientist, which you are all becoming throughout the course of this afternoon, you want to set in advance. Now the things that it learns during the process are called parameters. The things that you set up front are called hyperparameters. And there's a hyperparameter that we might want to set on our model here, which is to tell it that we do indeed want to fit the y-intercept. Some linear regression models fix the y-intercept to 0, so we want to make sure that the y-intercept is going to be fitted as part of learning about the data. So we pass in another parameter, fit intercept equals true. And then we run that cell. So if you could all run those 2 lines of code now, make sure that scikit-learn is working, is installed, it's able to run at least that much, then I'll step on to actually fitting the data. We've now got our model. It's sitting there ready to learn. It's like a student who's just turned up at the beginning of class, doesn't know anything yet, but knows how to learn, but just needs to be given the information to extract the things that they really, really care about. Hopefully that's how you all feel, and you will learn something throughout this course. So in order to allow the model to extract the parameters of interest, which as I said are going to be the gradient and the y-intercept of the straight line, we have to show it some data. Now all models in scikit-learn have a nice consistent interface to them, and that's you type the name of the object that represents the model you've created, and you call the fit function on it. All models in scikit-learn have this fit function. As to the arguments that the fit function accepts, again, there's a good amount of consistency here, but it's important to understand the type of data that it expects you to pass in here. For a model like this, where we're showing it some data that we want it to learn from, and some more data we want it to learn to, i.e. the x and the y, the fit function is going to take 2 arguments, effectively x and y. But we can't just write x and y, we have to actually give it the data, which from above we've stored in our data object. The fit function expects the x argument to be a 2-dimensional object. That is, we can't just pass it a single list of numbers, we have to pass it a table of numbers. Now we're going to get our data from our data table, which we had above, and we would in principle want to grab our x column from that table. The only reason we can't do that directly is that the x column from our table is only a single column, and with pandas particularly, if you extract a single column out of a table, it gives you back a 1-dimensional object, basically a list of all the numbers. We want to tell pandas that we want to get a 2-dimensional data frame out of our larger data frame, and so we have to tell it we want to get a data frame which is made up from the columns x. Now in principle, if there were multiple, we would do x, x1, x2, etc. But in our case here, because our data only has one single x parameter, we just ask for a single x. And that is why we have these slightly strange looking double square brackets when we call the x parameter. That is to make sure that our x parameter being passed in is 2-dimensional. It should be a table of data. 1 row for every sample, 1 column for every feature or x value. The second argument that the fit function takes is, unsurprisingly, the y data. Now, in this case, it is okay with the y data being a 1-dimensional list because there is only usually 1 column of y data. For each sample, i.e. for each row, and I'll just scroll up, it is going to use all of the x's to work out what the y is. And then the next sample is going to find the relationship between all those x's and the y. So we're passing in our x data as a 2-dimensional table and our y data as a 1-dimensional list. At this point, we can go ahead and run that cell. And in that split second, it has gone and done the machine learning. It is computed some algorithm. I think it uses ordinary least squareds to calculate what the line of best fit through the data is. And it has now saved the results of that into this model object. So by calling the fit function, you have performed the machine learning step. Because we only got 50 data points and a 1 x value and 1 y value, it only takes a fraction of a second. With more complicated models, it could potentially take hours to run this single line of code if you were doing something a lot more complicated. If you could all run that line of code as well now, make sure that's working for you, and then I'll step on to the next section. The learnt parameters are now inside this model object, and this might be a case of you've got to trust me, they honestly are inside there, but you absolutely should not just blindly trust me. You should be asking the question, how can I get access to those parameters? It's all very well it having learnt about the data if we can't then extract out the stuff that it's learnt. The number one way that you get access to the data from the model is by calling the predict function. So the predict function, after the model has been fit, can then be passed in to X data and will make a prediction of what the corresponding Y data should be based on the model that it's been able to create. Given that we've got a straight line, we will be able to plot a straight line of what our predictions look like simply by grabbing the upper and the lower points that we care about and then drawing a straight line between those 2 points. So let's grab our 2 points that we care about, our upper and lower bounds on the range that we're looking at. So we can get the lower bound with data, from the X column dot min. That's going to be the smallest X value, and then data from the X column dot max. Let's stick that inside a list. It's a 2-item list. And then for sake of getting things in the right shape, we want to turn this into a table of data. So I'm going to do the similar thing to what I did before, frame, where I make the X data into a data frame. I'm going to call that X fit. Because I'm now using the data frame, I've got to from pandas import data frame. The reason I've done this data frame thing here is because we're creating X data again. And the same as with the fit function, our X data had to be in a 2-dimensional table. Likewise, with the predict function, our data has got to be inside a 2-dimensional table. We can then pass that to our predict function. It's going to make a prediction once for the minimum value, give us back what the corresponding Y value is, and then it's going to do it again for the max value and give us back the corresponding Y value. So this will give us back 2 pieces of data, which we are going to save into Y predicted. Best way to visualize things is to plot them. So let's do data.plot.scatter, exactly the same as we did before, X and Y. So we're plotting our overall data there. Save that plot so that we can plot the other data on the same pair of axes. And on this second pair of axes, over the top of the scatter plot of our data points, we are going to plot a straight line with the X values X fit and the Y values Y predicted. I'm also going to set the line style to be a dotted line. That's how you do that in matplotlib. So now if we run this, we get our original data as we had it before, but we also get plotted a dotted line showing what the model has made a prediction of. This dotted line has been created by predicting a point down here on the bottom left and predicting another point over there on the top right, and it's drawn a straight line through the 2 of them on this line here. So visually, it looks like it's doing a good job of predicting what our data is. The question is, a visual representation of our data is only so useful. Often we want to be able to extract numerical values from our data. In order to do that, the data has been saved onto this model object, and so we can extract that out. So I'm going to make another cell here and have a look at some of these pieces of data. So the coefficients, which is going to be the gradient of the line, are saved in an array on the model object, which is in this case got the value, so 1-element array with a value of 1.977. The reason the coefficients are returned as an array is to have a consistent interface in case we were fitting over a polynomial of some kind, in which case there will be multiple coefficients here. So since we've only got 1, we'll just ask for the 0th coefficient. And we can also have a look at the intercept. You'll notice that both of these attributes have got an underscore at the end. That's a scikit-learn convention used to represent attributes which only exist after the fit has been performed. So if you ask for these and you hadn't yet run fit, you get an error. The underscore tells you that this is a learnt attribute, or learnt parameter, I should say. Have a look at what the intercept is. No, I did that wrong. Have a look at what the intercept is, and it says it's minus 4.903, etc., etc. Now I expect on your computer you've got exactly the same numbers as these, and that's because this is a relatively deterministic algorithm. There isn't much randomness going on, and so since we've started with the same set of data, we run basically the same version of the fitting package, we end up with exactly the same number at the end. If you were on a different version of scikit-learn, maybe even on a different version of Python, you might end up getting slightly different results here, but they should always be the same to a certain number of decimal places. So this is telling us that we've got a line that is being represented more or less by the equation y equal to 1.977 times x minus 4.9. We look at minus 4.9, we see on the plot above that it does probably hit the y-axis at minus 5-ish, and the gradient is about a gradient of 2. So these numbers are fitting with our expectations. As it happens, this data was created from a gradient of 2 and a y-intercept of minus 5. So the slight difference here is down to the randomness that I introduced into the data. So have a go with doing that yourself. Run the same model above and try fitting it all out. The exercise that I'm showing you here is at the bottom of the fitting data chapter. All of our exercises are in these yellow boxes. So have a go at fitting that data, making sure you get the same thing above. Once you've got that working, have a go at doing the same process on a different data set. So scikit-learn comes with a bunch of example data sets, which you get through sklearn.datasets. There's one which represents diabetes patients. So try doing a line of best fit between the BMI column and the target column inside there to see if there's see what the relationship between those two parameters is. I'll give you a few minutes to have a go with that, and then we'll carry on to the next section. I'm going to go through the answer to the diabetes example now on the screen so that everyone has an example of how it's working. As with all of the exercise today, there is an answer linked in the notes, so you can always check that if you're struggling, but sometimes talking it through is a better way to learn. So down here, I'm going to make a few cells, and I'm going to paste in the bit of code that was basically given to you. Here we're calling the load diabetes function. It's giving us the data. The title, the column headings are coming from the function's feature names attribute. And we also take the target column. This represents the Y that we were talking about before, and we put that into the target column. When we look at that, we get some data that looks like this. So we've got age, sex, BMI. That's the column that we're interested in for doing our linear regression. A bunch more parameters, which are documented, but I don't know what they mean, and a target column. So the question we're asking here is, what is the relationship between the BMI column and the target column? The first thing to do there, really, is to do a fit. Now we do that using AX equals diabetes.plot.scatter BMI and target. Have a look at that and we see there's definitely a loose relationship between the two of them. It's a very wide distribution, but there's definitely some kind of relationship there. But we want to be able to extract out a numerical value which represents the two of them. So let's do that same thing we did before. Model equals linear regression. We want to make sure we're fitting the y-intercept. And then we fit our model with model.fit. Here again, we need to make sure that our x values being passed in are two-dimensional. So we do diabetes square brackets, and then we want to do a second pair of square brackets and ask for the BMI columns. As our y value, as our target we're aiming for, is our y-axis, which is going to be diabetes target. If we run that, it's going to fit the model, but we want to also plot our model. So I'm just going to copy and paste these two lines of code. They're exactly the same things we did before. We get the minimum value from the BMI column and the maximum value. We make a prediction for each, and then we are going to plot that prediction onto the same axis. Line style equals dotted line, and this time let's make the line red, make it a bit more interesting. And there we go. It's made an estimate of the relationship between those two things, and it's plotting the line. So you see here, no matter what data you've got, As long as you've got an input column and an output column, you can always extract the two of them. Sure, there's a question in the chat there, Abada, asking, can you explain why the X data should be in a 2D array? So the reason for that, and I'll get onto this in a bit more detail in the next section, is that in general, your data is going to have multiple measurements you made, and then you want to make one eventual prediction. So the example I use in the next chapter is that you're maybe trying to come up with a model which is able to predict the price of a house. And so you might want to work out what the price of a house is based on the number of rooms in the house, the size of the garden, and how many schools there are nearby. So you've got three things of interest that you've measured, and based on those three things, you want to be able to predict what the house price is. And so because in principle, your thing you're learning from can have 2, 3, 4, 1,000 different columns or features that you're looking at, the fit function in scikit-learn will always assume that your X data is going to be a set of columns. It's going to be a two-dimensional array. It's going to have a row for each sample. In this case of the diabetes, each sample is a person. In the case of the house price data, each sample is a house that you've measured the number of rooms of, the size of the garden, and the number of schools in the area. So because the fit function is always assuming this is going to be two-dimensional, even if we only have a single column of data, we have to pass in a two-dimensional object which represents even a single column. To explain how this syntax works a bit more, let's have a little look. So let's look at diabetes. Let's look at the whole thing. There we go. So that's the whole table. It is two-dimensional because it's got rows and it's got columns. A row in these tables is often called a sample or an example or a measurement. In general, each of these column headings are called a feature because they're a different feature of the data. You have an age feature and a sex feature and a BMI feature. In the table here, we've also got the target, which is, well, sometimes it's called the target, sometimes it's got other names, but in general, we're going to call it target here. If we look at the number of dimensions of this, which you can use using ndim, it tells us it's two-dimensional. If we look at the shape of our data, we see it's 422 by 11. One dimension, two dimensions. So here we've got a two-dimensional table of data. We want to train our model based on the BMI column. So let's have a look at what that looks like if we just extract the BMI column. It gives us back a single column of data. These are the data in this column. The numbers here are just row labels. So we have a single one-dimensional column of data. And I can prove to you that it's one-dimensional by copying that code, pasting it, and doing ndim. And it tells us that it is indeed one-dimensional. We want to extract this same data here, but we want to have it represented as a two-dimensional object because fit always wants your data as a table with n columns. Whether n is 1 or 1,000, it wants it as a table of data. And so to do that, we do diabetes, square brackets, and instead of just doing a single object there, we can pass a list of column titles. So we can pass BMI and age and sex. And when we print this, we get out a subset of that table with just those columns in. If we look at the number of dimensions, of course, it's two-dimensional. Using this same syntax, we're passing a list in here, but we can pass in a list with only one item in, so we can delete those two things. We're still passing in a list, but it's only got one object in. But because we're passing in a list, pandas is going to give us back a table of data at the end rather than a single column. So that gives us back a table of data in contrast to the single column of data we got here. And that is happening because of that extra pair of square brackets. If we look at the number of dimensions of this, we see that this is now two-dimensional. So scikit-learn always wants the X data to be as a table because in principle it can have multiple features. In our case here, we only have one feature, but we are still having to pass it in of the same shape of data. Most programming tools have an assumption about shapes of data and so on because it makes their internal logic easier. If we only passed in a one-dimensional thing, it wouldn't know whether we were passing in a single column with multiple samples or a single sample with multiple features, for example. So I'm going to talk a little bit first, before we get on to other techniques, about what machine learning is, how it works, and how you can think about starting to apply it to your data. And by apply it to your data, I mean think about what it's possible to do with it, so you know what questions you can ask of it, so you can plan right from the beginning to use machine learning in your analysis by making sure you've collected your data in the right kind of format. But on the whole, there are two main classes of machine learning. We have supervised methods and we have unsupervised methods. Now, a supervised method of machine learning is one where you've got a set of features, a set of x's, and you want to, based on the values of those features, predict what the value of a target is going to be, what the value of y is going to be. So a supervised model is one where you're finding a relationship between x and y. You're trying to learn out how to get from one to the other. Remember that x can be multiple different features, so you're trying to see how to get from those data to the y target data. So that's what a supervised model is. Now, you can see the linear regression we were doing in the last section was one of those. It was a supervised model. We were trying to find the relationship between our x column and our y column. Similarly, with the BMI example, we were finding the relationship between BMI and target. Within supervised techniques, there are two main categories. Those fall into classification and regression. So a regression is what we were finding with our linear regression, hence the name, just there. Our target was a continuous value. Based on our inputs, we were trying to find out where on this scale our estimate was going to end up. With the house prices, that's a regression example because we are trying to guess what the price of this house is going to be. From £0 up to £1 billion, it's somewhere on that scale. That's the range of value we want to predict that we want to end up inside. By contrast, some supervised techniques are going to do what's called a classification. They're going to take the set of features, the set of inputs, and it's going to put them into one of a set number of buckets. For example, you might be trying to work out what species a particular kind of flower is. You take some measurements of it, and at the end of the day, you're not going to find out how much of one species or another it is. It is going to be falling into species A, species B, or species C, for example. So they're both starting with some features and trying to end up at some kind of target, but whether that target is quantized or continuous tells you whether you're doing a classification or a regression. So the thing we did in the last section was a supervised regression. Most of the time when people think about machine learning, they are talking about supervised methods. They are talking about these kinds of things where you're finding a relationship between your inputs and your outputs. If you're doing a technique where you're trying to take a picture of an animal and tell you if it's a cat or a dog, that's a classification. If you're trying to take some features about a person and trying to work out whether they should have a loan because they're going to be likely to or not pay back the loan, that could be a regression because it's giving you back a probability which you're going to interpret. The other major class of machine learning is what's called unsupervised. Unsurprisingly, given the other one was called supervised. Now, an unsupervised machine learning model is one which doesn't have a target. You have all your features, you've got all your x values, but you don't have a y. You're not trying to get to a particular place. You are just trying to understand some internal relationship between all of the features that you're putting in. It can be a little bit hard to understand how it can possibly learn anything if it doesn't know where it's supposed to end up. But depending on the kind of question you're asking, there are things that you can extract about your data. The two main classes here are clustering, where you're trying to find subsets of your population of samples and put them into buckets. It's kind of like a classification, but where it's working out its own categories. Or things like dimensionality reduction, where it just looks at your data and it tries to just simplify it in some way. So it's not trying to get to a particular place, it's just trying to reduce down the amount of information you have to think about. So these techniques are often used in concert. You might do a clustering before you do a classification or something like this. They're not, you don't just use one technique and call it done. You often have combinations of these things. But if there's no question on that first section there, then I'm just going to talk through now the process that you go through for supervised learning. Because supervised learning, as I said, is one of the most common techniques that get used. And it's often what you end up doing in your research or scientific contexts. You've made some measurements and you want to make a prediction because you don't want to have to run the real experiment every time, because experiments are expensive and difficult, or maybe they can't be run because they were time-based in some way. So you want to make some kind of computer model, which is going to represent what you think is happening in that experiment. So the supervised learning process is a fairly standard set of steps that you'll go through, and it all starts with collecting your data. Well, I suppose it starts with deciding the question you want to answer. Let's say, as I was mentioning before, that we want to have an example where we are predicting the price of a house. We want to measure how old the house is, how many rooms it's got, and the size of its garden. Those are all things which are easily measurable. Anyone can count how many rooms a house has, measure its garden, and look up on some records how old it is. But it does take an expert, or it takes the market, to work out how expensive a house is going to be. And it is a question you want to answer before you go into the process of trying to sell your house. You want to make sure you're going to get your money's worth for it. So in order to work out a model which is going to relate the price of a house with those features of it, we need to go out and collect some data to train a model on. So the first step here is to go out into the wild and find some real houses, measure their features, measure their ages, number of rooms, size of gardens, etc. And for each of those, we've got 3 features. So we've got 3 columns in our table. Each house is going to be its own row in the table. And those rows and columns, those features and samples together, those are what make up our X. Those are our things that we're going to be learning from. That is our input to our model. So we take those things, we measure our X, and we set that to one side. We write it down in our notebook. While that process is going on, for each house that we've looked at, we also want to work out what the price of that house is. Now, we only want to do that process for the subset of data that we are looking in detail at. So we do this as a one-off, just for this set of data. So an expert looks at the price of the house and assesses it, or maybe you look at the market records for recently sold houses and you do that slightly more intensive process, and we put that list of house prices in our Y column, so that each row now has the 3 features and a target and a Y. So now we've got all our data. We've done our initial data collection. We are now ready to start doing machine learning to it. The first thing to do before you just start throwing computers at something is to think about the kind of data you have, the shape of the data, the quality of the data, these kinds of things, and think about what relationships are there or do you want to discover between X and Y. In the example we had in the first chapter, a linear regression was just fine, but sometimes there's something more complicated. Deciding which model to use comes with experience and experimentation. It takes some time to discover what tools are out there and what possible things you could use to solve the problem you're trying to do. But let's say we've decided we want to use a linear regression, some kind of multivariate linear regression to represent these things. So we just choose our model, we import it into scikit-learn, let's say, and using our X and Y, we throw them at the machine learning. We let it do its thing. We call the .fit function, as we did before. The machine learning algorithm goes away and does its thing. We don't really have to care too much about how it works behind the scenes. We just trust that it's doing the right thing. At least at this point. Later on, you will want to understand more about how they work. But for now, we're happy just to learn it. Once it's finished learning about the data, we can now effectively throw our data away. You shouldn't. You should keep your data, but you no longer need it for that model to do anything useful. That model has internalized and simplified the relationships between that data down into a few internal parameters. And so now we can use that model to make predictions. It will look up the value of those internal parameters, stick them into some kind of equation, and give us back the answer. So that means in a year's time, someone can come along to us and say, hi, I want to sell my house. We ask them how many rooms it's got, size of the garden, etc., etc., etc. We put those 3 numbers, which I'm going to designate X prime here for sake of argument because they're different to our X from before. We put those numbers into our model and it gives us back a estimate or prediction Y hat. Now Y hat is commonly used as the designator for a predicted value from a model. So you'll see that crop up quite a bit. Y hat is a prediction from a model. Now, Y hat is just a prediction. We don't know that it's correct. There is, for any given house, an actual price that that house is worth. It might not be calculable, or it might be hard to calculate, but there's a real value out there. And so in principle, there is a measure of how right we are. If we imagine that person sold their house the next day, we would immediately know how right we were. Now, the measure of how right you are is sometimes easy to calculate and sometimes it's hard, but usually you can go a long way by simply subtracting your prediction from your real value. Now, you don't always know your real value, so that's not always easy, but if you do, just do a difference between the two of them, and that gives you back what's called the residual. Now, the residual is, in general, a measure of how good you did. It's what left over, is what residual means. So I've gone through this section here just to give you an idea of some of the terminology, give you a sense of how the flow of data works, and when things are used and when they stop being needed to be used. Now we've got a sense of the general process that you go through when you're trying to discover relationships in your data. I think it's worth taking a little step back and thinking about, before we throw machine learning at our models, what we can do to discover information about them, because the shape of our data, the type of our data, often strongly informs both what models we can use and how we should go about applying them. And I think one of the really important things to look at when you've got large data sets is looking at the correlation between your data. Now, correlation is one of these things which I feel is oversimplified when it's taught. And so I'm going to go through now what I feel is a better explanation of what correlation is and how it can be useful without going into the maths and so on. And then we're going to see situations where that nuanced opinion of it can actually start being quite useful. So when you're taught correlation at school or university, you're often told the full description, but it's often very, very quickly simplified down to how linearly related are these two parameters. By that I mean, as one parameter increases, how much does the other one increase, and vice versa. As one goes down, how much does the other one go down? That's a useful measure of data. It's a useful thing to understand. One of its real powers is the fact that it's really easy to calculate. Finding out linear relationships between data is almost trivial. There's a good number of easy to use and implement algorithms out there for finding out what the linear correlation between two values is. So I'm not trying to diminish the value of linear regression, but I think there is more to be said about regression than simply how linearly related things are. So you see on the screen here, there's a single plot. It's got an X and a Y value. It's got a scatter in the middle. These two values here are strongly, positively, linearly correlated. As X increases, so does Y, and as X decreases, so does Y. So it's positive because they're both changing in the same direction. It's linear because there's no kind of strange shape to it. And they're correlated because, well, we've got a strong value for that correlation. But beyond linear correlation, I think there's more to be said. So I find it more useful to, instead of thinking about correlation in terms of as one goes up, how much does the other one go up, to instead think about in more detail how related the two sets of data are. Now, this is going to consume linear correlation, but it's a broader concept. So I like to think of it more in the sense of, if I know the value of one of the variables, how much do I know about the other? How much information do I have about Y if I know the value of X? So looking at this parabola plot on the screen here, if I worked out what the linear correlation of this was, it would probably tell me that it's 0. If you plotted a line of best fit through it, a linear line, it would just be a straight horizontal line going straight through the middle. So that would be saying that the linear correlation of these two variables is 0, and so there's no relationship between the two of them, or at least that single parameter would simplify it down to that point and would say there's nothing that you can say. If you know X, you have no information about Y. That's what linear correlation would tell us. Yet, clearly, looking at this plot, we know if we've got the value of X, we can make a really quite good guess about what Y is. If X is 8, for example, well, Y is about 15. There's no way that Y is going to be 0 or 30. It's going to be about 15. Likewise, if X is 0, then Y is going to be about 0. So there is definitely a strong correlation between these two things, but the linear correlation is 0. And this is why I think it's worth thinking more broadly than linear correlations. It comes into play as well because a lot of machine learning models are more than linear. They can discover superlinear relationships between things, and so us being able to describe them is a really useful thing to be able to do. In a more mathematical sense, the way that I like to think about correlation is really in terms of mutual information. And there's a really good, slightly mathsy Wikipedia page on mutual information, which describes this well, but it effectively comes down to how much information overlap or how much information sharing is there between X and Y. If there's perfect information sharing, then they are completely overlapping in the Venn diagram, and so they're exactly the same piece of data. If there's no information sharing, then that's saying there's no correlation at all. But if there's some, then you can find out something about Y from X, and probably vice versa. So thinking about mutual information and information overlap between your sets of data, I think is a better way of thinking about correlation than simply what is the single linear correlation value of these data. That said, we're going to jump straight into linear correlation because, as I said, it's really easy to calculate, so it's a good place to start. So I'm going to make a new notebook. I'm going to call this one correlation. And I'm going to load up some data. I'm going to import some pandas and numpy to get some data out. And I'm going to make a list of data, np.arange. This is going to make a range of numbers from 0 to 99. That's what the 100 means. I'm going to make a second variable, which is going to be exactly the same, except this one is multiplied by 2. If I plot this data by sticking it into a data frame, and have a look at the top of it, this is what we see. So we've got one column A, one column B. The numbers are both going up as the other one's going up. So immediately you're probably thinking, well, these are strongly positively correlated. That's a good place to start. So you're almost definitely correct. But with any data like this, there's some other things that we can learn about it along the way using the tools that Python provides. So this data frame df, before we jump in and calculate the correlation, there's a function called describe, which is worth knowing about, which gives you very basic summary statistics about any given data frame. So when we run that, we see printed out how many values there are. There's 100 because we asked for 100 of them. The mean is about 50 of the first one. The second one, the mean is about 99. That's because the first one goes from 0 to 99, and the second one goes from 0 to 200-ish. Doing this describe thing is always a useful thing to do because it gives you a sense of the skew of your data, because you've got your percentiles, your standard deviations, things like that. So it's always worth having a look at your describe just to make sure you haven't got any weird values, weird outliers hanging out. It's a very nice, easy way to spot them. So a question there about why do we use a dictionary for this data frame here. I did that so that I could take this value here, which is this first column, and this value here in this second column, and give them column names so that it would be called A and B. If I did it just by passing a list, they wouldn't have had column names, and so we would lose track of which one was which. Once we've got our data frame, as well as calling describe on it, we can just go ahead and call the correlation function, or as they call it, core, because typing elation is far too much work apparently. And it gives us back a nice small table summarizing the correlation between the two values. First thing to point out on a correlation table like this, you might have come across these before, but if you haven't, then the diagonal terms here are telling us what is the correlation between A, and it's 1.0. And the second value here is telling us what's the correlation between B and B, also 1. We'd always expect the diagonal terms to be exactly 1 because each data set is always perfectly correlated with itself. It is the off-diagonal terms which are the more interesting ones. In this case, they are also still 1.0 because A is perfectly correlated with B, and inversely, B is perfectly correlated with A. Each side of this matrix here is often the exact copy of the other triangle. So the top right is always the same as the bottom left. So have a go at that yourself. Run those commands, make sure it's working. Then try tweaking your A and B up here so you get a pair of data which are inversely correlated with each other. So they've got negative correlation such that you end up with -1 on your off-diagonal terms. Okay, great. Abada posted in saying that you just multiplied that by -2. That's exactly the right idea. So, as I was saying, positive correlation is if one goes up, the other one goes up. Negative correlation is if one goes up, the other one goes down. So if we make that to be going down each time as A is increasing, B is decreasing, when we look at the correlation, we get -1 on the off-diagonals. To get anything which isn't exactly -1 or 1, we'd have to add in some more interesting variants to our data, which require some random functions or just manually doing it. So instead of doing that by hand, let's have a look at some real data and see what we can learn about it. And also how we can do correlations between more than just one column and another column in a boring made-up data set. So again, we're going to have a look at scikit-learn's datasets area. This is where we got the diabetes dataset from before. But this time we are going to import the fetch California housing dataset, and we are going to save that as housing data equals that. So we're just grabbing the data there. I'm then going to put that housing data into a data frame so that it gets presented in a slightly nicer looking way. Data frame housing data dot data as the data in the table itself, and housing data dot columns as the column names are the feature names of that data set. I'm going to call that housing, and I'm going to print out the first few rows of it so we can see what it looks like. So what we have here is a table of data. We have 1, 2, 3, 4, 5, 6, 7, 8 features. The target column is loaded separately, so these are all X. This is basically a big table of our X data. We've got 8 columns and we've got some number of rows. We'll have a look in a little bit and see how many rows there are probably. The meaning of these columns are each row is a census block in America. So it's 100, few hundred people or something like that. So it's some number of houses, but a small enough number that the variation within that little block should be quite small. And we're finding out for each of those blocks what the median income of the people who live there is, the average age of houses, average number of rooms, average number of bedrooms, the population of that area, so 300 people, 400 people, that kind of thing, average number of people per residence, and also where that census block is, so we have a bit of context for that stuff. So before, when we did the correlation function, we took our data frame and we plotted the core function for it. We called the core function for it. And that gave us back for each column the correlation with every other column. With only 2 columns, that's pretty boring. But the exact same syntax works no matter how many columns you have. So if we do housing.core here, it's going to think a little bit harder about it, but it should only take a fraction of a second. And it gives us back a table of data. This table has 8 columns and 8 rows. Again, the diagonal terms are all 1.0 because the age of a house is always correlated with the age of the same house. So we get 1 on all the diagonals, on this main diagonal, sorry. Again, notice that the 2 different halves of the matrix are exact copies of each other. So this value here, minus 0.11, is the same as this value here, minus 0.11. So you can often get away with just looking at one half of the table. Because we've now got this as a real pandas data frame, we can drill down and find out more information about what's going on. So we can, let's actually call this core. and refer to that variable. So we can ask for the median income column. That's going to give us back that one column. Oh, I didn't run that cell. There we go. That gives us back that one column. And then from that column, we can extract out a row like average rooms. So this is going to tell us what is the correlation between the median income and the average rooms in this particular data set. And it gives us a slight positive correlation. So it's telling us that on average, as the income increases, so does the number of rooms, but it's not a solid increase. There's a fair bit of variance to it. So have a go running that code yourself, get that loaded in. And what I want you to do is to have a look at this table of data and see if you can pick out by eye what the most negative and the most positive correlations are in that table. See if you can do it by eye. If you want to, you can have a go at writing some code to do it. It's perfectly possible. But doing it by eye is the first step in that process to get a sense of how this stuff works. So I'll just give you a minute or so to look at that by eye. If you want to have a go with the code, feel free to do it now or later on. And then we'll have a little discussion about what we're seeing here. Could anyone tell me what they think is the strongest negative correlation? Okay, great. And what is the strongest positive correlation? Yeah, rooms to bedrooms is a strong correlation between a strong correlation there in the positive direction. Now that positive correlation makes a lot of sense. We'd expect that if houses have got more bedrooms, they've therefore got more rooms and vice versa. However, that process probably wasn't painless. Scanning through a table by eye, going up and down these columns one by one is hard work. You have to peer into it and try and look at the numbers, remember what the biggest or smallest number you've seen is, and so on. And so, as you all know, plotting large amounts of data as a table isn't the right way to do it. We want to visualize it in some way and make it easy for our eyes to see. So we are going to plot this same set of data here, but in a visual way. So let's have a look at how we do that. I'm going to use a package called Seaborn, which is a plotting package which builds on Matplotlib but adds in a bit more functionality, slightly nicer API at times, but it adds in at least one default, easy to draw matrix plotting of correlation functions, which is going to be useful for what we want here. We're going to import it as SNS because that's convention. And we're going to do sns.heat map, and we just pass in that table. In order to make this look a bit nicer, we're also going to give it a color map so that 0 is a nice neutral white, strong numbers are going to be blue, and strong negative numbers are going to be red. So to make a diverging color map, we are also going to do sns.diverging palette. And this is one of the things that Seaborn provides, is nice, easy to use functions like diverging palette, where you specify where you want to start, where you want to end up, and that you want it to be used as a color map. And we pass that to our plotting function with cmap equals cmap. And when we plot this, we get our, actually I'm going to do 220 because it's a slightly nicer blue. There we go. So here, much more easily, we can immediately spot our positive and our negative strong correlations. So looking at the upper end of this graph, we see that blue is used for a correlation of 1. We see strong blues along the diagonal. We also see a next strongest blue between average bedrooms and average rooms. So we're immediately seeing there's a strong correlation there. We didn't have to scour the numbers, we just plot it and we get it out straight away. And so I would recommend the first thing you do with your data is grab it in, look at some of the summary statistics, have a look at the correlation between them. It's worth looking at the table, but don't spend too much time on it. It's a good idea to go as quickly to a plot as you can, because you're going to be able to spot interesting things much more quickly. This here is showing the linear correlation between the variables. So it's telling us that the linear relationship between average bedrooms and average rooms is, 0.32 we saw before, so it's relatively strong. But it isn't necessarily telling us the whole story. We saw before that linear correlation is only a part of how you can describe the relationship between data. it doesn't give us enough information to learn everything about it. So we want to be able to look at the relationship between these variables in a more nuanced way than reducing it down to a single number representing the linear correlation between the two variables. Linear correlation gives us a nice square rectangle on this plot, but we want to get some more information, more detailed information about what's going on. And so pandas provides a function to help us do this, and it is called scatter matrix. So pandas, which is how we've been loading our data, has got a plotting sub package, and from there we can import scatter matrix. You use scatter matrix. I'm going to assign it to a variable here because otherwise it's going to print a load of nonsense to the screen with scatter underscore matrix, and we pass it housing. By default it's going to plot it quite small, and so I am going to pass in the fig size argument, which accepts for some reason in inches the size of the plot, and so let's make it 16 inches square because I know that's about right. This will take a minute to plot, so do be patient with it. It's plotting all of the data, but it will eventually get there. So have a go at doing that yourself, get that plot up, and then I'm going to talk through how you read this plot because it's not always immediately obvious. There we go. So that's showing up on my screen now. So while yours is running, I'm actually going to switch to the notes and get the picture because it's easier to make it big. That is the plot of all of the data. It's effectively the same information as we had before with the correlation matrix, but instead of the relationship between each variable and each other being summarized down to a single variable, it's instead plotting the scatter plot of the relationship between the two. So the best place to look first is at the average bedrooms and average rooms column and row. So that's row 4 and column 3, for example. They had a strong positive correlation, and looking at the data here, we can see why. There is definitely a longitudinal blob going from the bottom left towards the top right. That is therefore making sense. As one goes up, the other one goes up. The linear correlation is strong, and so we're seeing something going on there. But looking at the other parameters on this plot, some of them are definitely a bit more nuanced than just a longitudinal blob. For starters, many of them are very, very skewed distribution. In fact, almost all of them are very skewed distributions. The easiest way to see the skew on the distribution is to look at the diagonals. Looking at the top, very top left square, for example, there we see what would be the scatter plot between median income and median income. They realised that actually there's no point in drawing that scatter plot, and so they've repurposed the diagonal terms on this plot to be a histogram of that variable. So this here is just a distribution of how many entries there are with a median income that's at the low end, at the medium end, and then up towards the high end at 15. So you see here there's a skewed distribution slightly towards the bottom end, but it's not completely skewed across. House age is also nicely balanced. House ages go up to about 60 years or so that's traditional American houses not being very old. And you see many of them are much, much younger than that. When we got into the average rooms and average bedrooms graphs, however, we see there's a very, very skewed distribution. So much so that it looks like it's entirely inside the first bin and nothing in any of the others. Now it can't be there's nothing in the others, otherwise those bins wouldn't exist. It's simply that this first bin, if you look at the x-axis, is covering everything from about 1 room up to 10 rooms or something. And I think it's fair to say that most houses have 10 or fewer rooms. These larger entries up here, of which there are many fewer, will be mansions or tower blocks or mistakes in the data, potentially. So those are very, very skewed distributions. Down in the bottom left, we see there's sort of the distribution between median income and latitude. There's some structure here. It's not linearly correlated in any sense, but there's definitely some information there. So there's something that we can do with that, potentially. There's something that a machine learning model could discover about that relationship. The last thing to point out on this plot is I was asking before if you could point out what the strongest negative correlation on that table was, and you all pointed out that it was the correlation between latitude and longitude. And that doesn't necessarily make sense to me. Why would the latitude and longitude be correlated on a table like that, on a piece of data like this? We don't expect, if you think about a map of the UK, that as the latitude goes up, the longitude should go up, because most places are kind of square blobs. Most geographical entities are roundish. But yet here we were seeing a very, very strong negative correlation. And more interestingly, that is consistent with what we're seeing in our scatter plots here. We see a very strong negative slew of data going from the top left to the bottom right when we're looking at our scatter plots down there in the bottom right. Now, has anyone got any ideas why we might be seeing this kind of correlation between latitude and longitude on this data set when we wouldn't normally expect there to be any relationship between them at all? Has anyone got any ideas? So Joe's saying it could be the coast. Yeah, so absolutely. There's some geographical things going on here. Clearly, where the coast is going to come into effect. It's going to bound the data in some way. So that's going to affect stuff. But the UK has a coast, and I don't think the UK would have this kind of correlation. Anyone else got any other ideas? Yeah, okay, so Abada's hit the nail on the head. Think about it for a moment. What do you get if you plot the longitude against the latitude of something? What you get is a map. If you plot the longitude and latitude of all of the census points on a grid, you get a map of all of those census points. It so happens that California is a shape which goes from the top left to the bottom right. It's an artifact of the location as to where this data was collected. This same data set in another state in the US, even with very similar conditions, because it would be a different shape, would have completely different correlation between its latitude and longitude. It is a particular feature of this data that we're seeing this. It's not necessarily something that we would expect. So we've accidentally drawn a map here without realizing what we were doing. I believe that it's the one on the top right that's the map and the bottom left is something else. In fact, if you look at it, you can almost see San Francisco going around the bay, though it's a little bit blurry due to some desert and mountains that get in the way a little bit. Yeah, exactly, Jafe. It suggests people on this one live in a line between those two things, but because we've taken a subset of our data by choosing California, it's kind of imposed that condition on the data when it wouldn't necessarily be there in the first place. It's not a natural thing, it is a data artifact. And this is something that's worth being really, really careful about when you're collecting and analysing data. We could have looked at our data here, thought that this was just a spurious bit of correlation, ignored it, carried on, trained a model based on this stuff to predict what the price of a given house would be, based on its longitude, its latitude, its occupation, the number of bedrooms, etc. We get a model which predicts it really well for California. We do our testing and our validation, and it would all be working well. Even if we took that model to somewhere else in the US, which is similar-ish, somewhere like, I don't know, New York or Washington, you would apply it and suddenly the whole model would collapse and fall apart because the longitude and latitude data has been baked into the model when really it's not relevant to it at all. It's found a relationship there, but it's not a general relationship. It's only a relationship which is specific to the place where the data was collected. It's a Californian relationship. It's not general. So that's a really obvious example once you see it. But the thing to remember is that all of your data is biased in this same way. You always have to be careful about what implicit or explicit assumptions have gone into the data collection, the data sampling, and what models you've chosen. This one here, you can spot it quite quickly. It jumps out when you look at the correlation. You see that there's some structure to it when you look at the data scattered on a plot like this. But you're not seeing it in the other parameters where there is also likely some data relationships which are slightly more hidden. So it's always worth being careful, thinking about where your data is coming from, how you're choosing to analyze it before you put it into your models, and where you then use that model, both elsewhere in the world and over time. Of course, a house price model isn't going to work if it was trained in the 80s and is being used in the 2020s. It's going to give you the wrong answer. All models have bounds, and part of your job as a data scientist is to think really carefully about what those bounds are, both to make them as broad as possible and to understand them so that you don't use a model in a place that it shouldn't be used. So the last thing I wanted to mention about correlation now is why we care about correlation in the context of machine learning. So there are two kind of competing ideas when it comes, or two competing concepts when it comes to correlations. The first is that between the features that go into your X, the things that you're training your model based on, for example here, average rooms and population, we don't want there to be a strong correlation between those two parameters. And this comes back to thinking about it in terms of information sharing. If we looked at average bedrooms and average rooms, they are strongly positively correlated. So we could train our model ignoring one of the two of them. So we just do it with average bedrooms and we'd get perhaps a good model coming out. If we then add in the average rooms parameter, we're not going to be adding much more information into our model because the information overlap between something that's already there is quite large. So we're adding in more data, we're adding in more processing time, but we're not adding in more information. And so that's going to make our model train slower, potentially behave worse, for very little benefit. So looking at the correlation between your variables and thinking about what variables you no longer need, that you can get rid of, or that aren't going to give you any useful information because maybe their skew is so much that they are all inside one bin and you're never going to be able to see anything, is a worthwhile exercise. There are techniques you can do to re-parameterize your features. There's things called dimensionality reduction algorithms. For example, principal component analysis can work out a new set of dimensions which don't have correlations between them, which are orthogonal to each other. And that's a kind of technique which you might want to apply to your data, and there's some information at the end of the course about where you can learn more about that. The other thing to think about with correlation is that while you don't want correlation between your various input values, you do want some kind of correlation or mutual information between a feature and your target. In fact, you need information overlap of some degree between what you're putting in and where you're trying to get to. Otherwise, there's no predictive power. If we were putting into this plot here the favourite colour of the people in each of those areas, that would have no correlation whatsoever with the price of the house. And so that would be a useless piece of information to put in. So looking at the correlation between your inputs and your output is worthwhile as well, because if they've got a strong correlation, then you're going to be able to get a lot of information out of it. And by strong correlation, I mean more than just a strong linear correlation. I mean a strong correlation in the broader sense of what kind of structure is there to the data. So between your features, you don't want correlation, but between your feature and your target, you often do want correlation. The next technique I wanted to cover was clustering. So if you remember near the beginning of the session, I was talking about the different kinds of machine learning. I was saying there was the supervised techniques, which have an X and a Y, and you're trying to find the relationship between X and Y. And there were the other techniques, which were the unsupervised techniques. And these are tools where you show the algorithm your data, and it just tries to learn some kind of information from the data or extract some kind of internal data from it. Now, clustering is probably the most famous example of unsupervised learning. And when I was first learning about unsupervised learning, when it first came across the concept, I was very confused by the whole thing because I couldn't understand how you can have a computer algorithm which learns about your data without knowing where it's supposed to end up. So hopefully I'm going to be able to show you how that is possible and how it works and the kinds of questions that you can answer about it. So we're not going to worry too much about the exact technical definition of how k-means clustering works. We're going to dive in and start just doing stuff with it, but I will then probably refer back to this and explain to you about how the way that this algorithm is implemented imposes certain limitations on what's possible to do with it. So I've made myself a new notebook here, and so I'm going to start off by making some data. Again, I'm going to start from scikit-learn. And scikit-learn's datasets module, as well as having built-in datasets like that California dataset or the diabetes dataset, also has some functions which allow us to generate data, sort of generate toy data. So in there is a function called make blobs. Can I just check that people can hear me okay? Someone in the chat was saying they couldn't. I'm assuming Lester can since he's narrating. Yep, Lester can hear me at least. So, okay, great. Welcome back, 7. So we've got our make blobs function. We can call that function. And it is unsurprisingly going to make us some blobs. There's some parameters we can pass in, of course. For example, how many sub-blobs do we want? How many data sample points do we want? And we want to do a largish number like 500. Then we tell it how many blobs we want. It calls them how many blob centers do we want, and we tell it that we want, let's say, 4. And because it's going to be generating these blobs randomly, and I want to first of all make sure that you're seeing the same random as I am, I'm also going to set the random seed. Now the random seed will make sure that while it's, no, the random state, sorry, will make sure that while it's technically kind of doing something pseudo-random, it's all going to be starting from the same place, and so we're all going to end up with the same set of pseudo-random numbers. And through extensive research before when I was writing the session, I found out that 6 is a good number. So let's go ahead and just use 6 for now. This returns 2 variables. It returns the data, i.e. the actual samples that make up the blobs, as well as which cluster each of those blobs originated from. So true labels. You can think of this as your X and your Y. I was saying before that since this is an unsupervised technique, we're not going to be using Y, and indeed we're not. We're going to not use this true labels variable at all in the training of our model. We're only going to use it to check how well we're doing, basically, if at all. So it's there as a cross-check for our educational purposes. It's not being used by the machine learning algorithm. So you run that and it generates the data. We then want to have a look at what this data looks like, because I'm sure you're all having trouble visualizing exactly what I'm talking about here. So let's go ahead and do a plot. I'm going to put the data into a pandas data frame first, because I like the pandas plotting interface. If you're comfortable with plain old matplotlib, then feel free to use that, but I like the pandas model. The points are then going to be that same data we got back from the makeBlobs function, but passed into a data frame. And I'm going to label the 2 columns as x1 and x2. Not x and y, because that would confuse with the features and targets that we had before. These are both effectively features of our data. We're not worrying about y here, because it's an unsupervised model, and so there's no y data. If the y data is anywhere, it's in this variable here, and it's going to stay there, out of the way, without us cheating by looking at it. Let's then plot our data, points.plot.scatter, and plot the x1 column against the x2 column. And there we have it. We have 4 different blobs, and we have 500 total samples, 500 little circles making up our plot. So first of all, I'm just going to ask you to just run those 2 lines of code. Make sure you've got that working, and you should see exactly the same blobs as I do. The same outliers, the same places of the centers, all that being identical. If you don't see something that's identical, make sure you set your random state correctly, and your number of samples and your number of centers. If you still get something different, well, it might be because you're on a different version, but I think they're relatively consistent. So have a go at doing that, give you 30 seconds, and then we'll move on to applying some machine learning to it. So we have here our x1 and our x2. These are input features to our model, in the same way that the size of the garden and the number of bedrooms are input features of the model. You might find that if you plotted size of garden against number of bedrooms, you wouldn't just see a spattering of data, you might see localized clusters of data in your output. Clustering is often used with large census data. For example, when you're doing a census for each individual or for each household, you'll end up with hundreds of different features describing that household. As a way of reducing the amount of information you need to keep about them, you might take a few of those features and simplify them down into some categories. For example, this is often done to put people into socioeconomic categories, whether they're working class, middle class, upper class, or whatever the new titles for these things are. Based on various features about the household to do with income and education and where in the country they live and so on, you might be able to cluster those features, find subsets of people which largely fall into one of a number of categories, and at that point you can effectively throw away those multiple features and replace them with one categorical feature, which is just which cluster are they part of, which can simplify analysis and also simplify human understanding of what's going on, because it allows you to take a whole bunch of features and put them into buckets and give them names. And that's useful for humans to understand what's happening. In order to analyze our data, let's go ahead and call the clustering algorithm. So again, from sklearn.cluster this time, not from linear model, but from cluster, we are going to import k-means. So k-means is a particular kind of clustering algorithm. It's called k-means because when you're deciding how you want to cluster your model, you decide in advance how many centers you want it to cluster it into. Another term for a cluster center is the cluster mean. And so if you want k means, you're saying you want k clusters, where k is a number between 0 and whatever. In our case here, we want to find 4 clusters, and so k is going to be 4. So we want to find 4 means. Same as before, we call our model like a function because it's a class we want to construct. There is a hyperparameter, which is the number of clusters. Deciding on how many clusters you want to use for your model is an art in itself. For example, when they were looking to try and work out how many different socioeconomic classes there are, and thinking in the last census we had, they changed the number and they reclassified them, they would effectively have tried a bunch of different number of clusters, seen which of those divisions worked best and gave them the best explainability, and then stuck with that. There's no absolute truth, except in the cases where it's been generated from something which has absolute truth, and we'll see an example of that a little bit later. In this case here, we generated this with 4 clusters, and so when we plot it, we also see there are 4 clusters, so of course k will be 4. We are then immediately going to call the fit function on it and pass in our points table. That is this table here, which is a data frame with 2 columns, x1 and x2, and 500 samples. I'm going to assign that to a variable. When I call this, it goes away, it does the algorithm, it's done the machine learning on those 500 points, and it's now put them all into categories. Have a go at running yourself that now, make sure you get that successfully running, and then we'll look about how we can extract the data from the model. Alistair's asking, can you get an algorithm to decide how many clusters there are? There are some techniques. I've never been very convinced by any of them. There's one where you look at effectively how good the fit is divided by the number of clusters, and you look at that for a different number of clusters, and you find the point at which that curve kinks most sharply. It's called, I think, the elbow finding technique, because when you plot the graph, it has a sort of an elbow shape, and you look for the point down in the bottom left where you've got fewer clusters but also fewer levels of uncertainty. If you actually try doing this, you'll find that there's never a single clear point at which you can say there are this many clusters. And so really, I would primarily say, let the number of clusters be informed by both your data and by the underlying model which you think that you're representing, and also by what data you're looking to extract. It often comes from starting at the point of, I want to divide my data into this many blobs, or I've looked at my data and I've seen it's probably this many. Beyond that, you can fiddle, and you might find that, oh, there's 10 or 11 or 12. And as you're changing those number of clusters, it could massively vary whether a certain sample goes into one cluster or another. And so you need to think about, what does that mean for your data? There's no magical way of doing it. There are tools that can help, but there's no magical solution. Once you've got your algorithm run, you've got your k-means object, which is containing the result of the fit. Let's go and see what we can see about what's inside it. So, k-means is the name of our object. Dot cluster underscore centers, spelt the American way, with an underscore at the end. Again, the underscore at the end is telling us that this is a computed parameter by the model. If we look at what that gives us back, it gives us back a NumPy array. I like to convert all of my NumPy arrays into pandas data frames because it prints them out more nicely. So let's make a data frame out of that and call the columns, because I know what the columns are called because they're the same columns we started with, are x1 and x2. Cluster centers, I'll use their spelling as well. And let's have a look at it. Oh, I've missed a bracket off the end. There we go, same data. If I array these so we can see them both on the screen at the same time, we look at cluster 0, it's saying that its x1 is at 6.5-ish, x1 is at 6.5. That's looking like it's lining up with one of the right-hand two clusters. Its x2 value is at -9, which if you look at the x2 axis is showing that that is pointing at the center of the bottommost cluster. If you looked at the corresponding x1, x2 coordinates for the other cluster centers, you'd see they would lie in the center of those three other blobs. Of course, doing that by hand, by looking at it visually, is no fun, so let's use the computer to do our job for us. We want to do the same thing we did before, points.plot.scatter x1 against x2. We're going to assign that to a variable, and then we are going to cluster centers.plot.scatter x1 against x2. So we're plotting the data points against each other, and we're plotting the data centers against each other. I'm going to tell it that we want to plot on the same axis. I'm going to say I want the color to be red for the cluster centers. I want the size to be a little bit bigger. These are all parameters I've worked out earlier because I prepared. And I'm going to use a marker of an X. So now when I plot this, we get our original clusters and we get a big red X printed on top of each of those clusters as to where the k-means algorithm thinks the cluster center has ended up. So have a go at that yourself, run those lines of code, get the cluster centers extracted and then plot it on a graph and make sure it's showing up something like this. I'll give you a minute for that and then I'll move on. Alistair's asking, how would clustering work on log scales? It would work fine. So if you take your data and you log your data, you can then cluster it fine. The thing to remember with k-means clustering specifically is that it works on a circular basis. The way it assigns points to clusters and then cluster centers to the center of the points that are on that cluster is with a traditional Euclidean distance, the Pythagorean distance of x squared or x1 squared plus x2 squared square rooted. And so it's implicitly working in a circle around the cluster center to find the points which are nearest to it. If your data has been logged and so it's skewed it in various ways, it may no longer be circular-ish data. And so your clustering algorithm is going to struggle to solve it. I've got some examples in a little bit of types of data where k-means fails and other clustering algorithms succeed. So we'll have a look at those in a little while and see the pros and cons of various algorithms and how you can go about solving it. And log scales come into play in that same kind of idea to do with transformations of your data. Yes, so I would try and make it so that the actual numerical parameters that are associated with each feature appear linear. So if my data was distributed exponentially, I would log my data so that the new parameter is effectively a linear scale of the exponent, so that my data now appears linear, even though the original data parameter was exponential. So by logging it, I've linearized it a bit more, made it more circular, made it more regular, so that clustering is going to work better on it. So we plotted the graph here by finding the where has it gone? The k-means.clusterCenters underscore parameter, which has given us 4 pieces of information because we set k to be 4. There is one other piece of information that the k-means clustering algorithm has provided for us, and that is k-means.labels. So you remember right at the beginning, if I scroll up, we extracted out our true labels. That was a number 0, 1, 2, or 3 for each of the sample points as to which cluster they were generated from. What the k-means algorithm has done is that when looking at this data without knowing what true labels is, it has, during its process, assigned each sample to a particular cluster, and it's remembered which cluster it's in. Obviously, throughout the algorithm doing its work, the label associated with each sample point is going to change as it's iterating towards a solution. But by the time it's finished, each sample will have a particular label. So we have a look at k-means.labels. We see it's a big old array where it's saying that the first sample is in cluster 3, whatever that means. Second sample is in cluster 0, whatever that means, etc., etc. Now these are effectively random cluster numbers. there's no reason to assume that the clusters are ordered from top left to bottom right. In fact, we saw before that cluster 0 was the bottommost cluster. But these numbers here do relate to our cluster numbers in our table here. So we can relate these two things together. But what we can do with that is we can use this to plot something. So let's again plot our points as a scatter plot. x1 against x2. We then are going to set the colour of each sample, of each small dot, to be based on its label that the k-means cluster has worked out it thinks it's part of. And so we do that by setting the colour to be equal to k-means dot labels. That works because matplotlib by default has a colour map which has a colour associated with each integer value. And so it's going to colour each of these based after whatever colour it thinks is colour 0, colour 1, colour 2, and colour 3. In fact, we can tell it which set of colours we want it to use by using color map. And let's use dark 2. And let's not print a colour bar because we don't need to see one, because we know what our different colours mean. And so now when we plot this, this is telling us which cluster the algorithm decided each point belongs to. And you can see that on the whole it seems like it's done a decent job. But there are clearly some points in here where there is potentially some ambiguity. First, my eye is drawn towards that yellow point, which is halfway between the grey and the yellowy-orange clusters in the middle there. To me, it looks like it's halfway in between. It's not going to be obvious which cluster it's falling into. It could be one, it could be the other. If we let the algorithm run for longer or for slightly less time, it might have ended up in a different cluster. Similarly for the green and orange points between the green and orange clusters, those 2 points are very close together, so you can easily believe that both of them could have ended up in one or both in the other, depending on how the iteration progressed. And as Alistair asks in the chat, how can you get k-means to infer probability distributions of which cluster each point belongs to? Not by default as it comes out. One technique you could do is, as the thing is iterating through, or once it's finished iterating, iterate it for a longer time, see if over that time period any points change from one cluster to another. And that's representing the clustering algorithm being unsure as to which cluster it belongs to. You could then look at how much time it spends in one cluster or another and assign to that some kind of frequentist probability as to which cluster it belongs to. But I don't know for sure whether that is necessarily statistically rigorous, but it would certainly give you a featureful idea of which points are the contentious ones. So what I'm going to ask you to do now is, as you've all been doing, follow through and do these copy the code examples that I've been doing. But if we have a look on the course notes, the first set of exercises on here, just after that clustering section, first of all have a go at running that through again, but try changing the random state of the original blob generation. You have to rerun the random state and then rerun all of the cells afterwards. See how that affects both the original distribution. See what happens in the situations where you end up with blobs overlapping, how well the clustering algorithm is able to distinguish the two of them. Make sure you understand about what's going on there, and if you have any questions, do please ask in the chat. Once you've had a little play with that, move on to exercise 2, where we're going to load in this iris dataset, which is from the scikit-learn datasets library. There's an iris function. You can load the data there into a data frame by copying this code here. So once you've got this iris thing, and then have a go at doing the clustering on this iris dataset. I do note this iris dataset has 4 features. I cheated a bit here with our x1 and x2 because it's easy to plot x1 against x2 on a 2D plot. Since the iris dataset has got 4 features, you'll have to think a bit hard about how you plot it. And as a trick, I'll remind you that you can use the scatter plot stuff we did for the correlation section on the page before, scatter matrix I think it was called. And if you get to it or you want to have a go, there's also an optional third exercise at which you can start looking at the inertia of these objects. I'll go through the answer to the exercise afterwards to explain what's going on, And exercise 3 comes on a little bit to the question about knowing how many clusters you should use and the techniques which I don't think are always that useful. Have a go with those, spend a few minutes on them, and let me know in the chat if you have any questions. So Serban's got a question there and says, when two blobs are very close, it separates them linearly. So let's have a look at what's going on there. So let's do random state. There we go. So when we look at the centers that come out of this. Oh, I need to rerun the algorithm. We see that it's put the two centers in the middle of what are probably the two blobs at the top of that section there. If we look at how it's assigned the labels, however, we'll see that the line between them is very much a straight line. And so what's going on inside k-means is that it keeps track of where the centers are as it iterates through. They start randomly. It then looks for all of it looks at each sample and works out which cluster center is nearest to it. Based on all of the samples which are therefore nearest to a given cluster, they will become part of that cluster. It moves the cluster center to the average of all the points in there and then iterates that process again. But because at the core of that, it's looking to see which cluster is nearest to a given data point, you end up with very, very straight lines of separation between cluster centers. This is very similar to a thing called Voronoi tessellation, which is a really interesting way of dividing up a plane based on random centers. You get a very similar thing happening here with k-means. And so even though our metric is circular, in that it's circularly isometric, you end up getting straight lines separating your clusters because along that line, it is equidistant from one center and the other. And that's why you get a nice sharp straight line between the purple and the brown clusters down here, for example. That's maybe a better example. These two clusters are very close together. It's not obvious to me at all how it should be able to distinguish those into two clusters. It's probably just put two there because there are more data points in that top left cluster. And that means when we plot it, we again see there's a very straight line of separation between the grey cluster and the purpley cluster. Again, this is due to the metric that's being used. It's which cluster center am I nearest to? So you end up with a straight line separating the two of them. Let's have a look at the iris dataset next then. So this was exercise 2. So let's start by going from sklearn.datasets import load iris. And then I'm going to copy the line that I gave you, which is loading that into a data frame. And let's have a look. So here we have a table. It has 150 samples and it has 4 features. Based on those 4 features, we want to be able to work out what the species of this is. So we know in advance, and in fact we can find out by running asking it for the number of target names, number of categories, number of classes at the end, and have a look at what that is. And there are 3, so there's 3 different species here. And we want to use these 4 features to group each sample into one of 3 clusters. Once we know where the cluster centers are, we can then bring along new fresh data from the wild and work out which cluster center it's nearest to, and therefore make an estimate as to which iris species this flower we've just found in our garden is, for example. So we are going to call our k-means function again, and we are going to pass in n clusters equals number of iris species. So this is a situation where we've worked out in advance how many clusters we should have because we know how many species we've measured our data from. And as long as any new data we put in belongs to one of those 3 species, this is going to work well. Then we fit it by passing in the iris table of data. I'm going to assign that to, again, I'm going to call it k-means because I'm unimaginative. That's now done the algorithm. It's worked out how these things are related to each other. That means we can now plot the scatter matrix because we've got multidimensional data. It's good to have something which can represent that multidimensional data. I'm going to plot our iris. I'm going to set the fig size to be, again, 16 by 16 to make it nice and large. I'm going to set the color based on the calculated labels from the algorithm. And here we have our iris data. So we have, again, I'm going to switch to the notes to see this picture because it's going to be easier to make large. We have our 4 features. Here we have the sepal length and the sepal width. Sepals are part of the flower in some way. I'm not a botanist, don't really ask me. And we've got the petal length and the petal width. I know what petals are, but I don't know how they're different from sepals. So we've got the length and the width of 2 different parts of the flower. And we have taken measurements of 150 flowers, and we have tried to work out, based on how those different variables relate to each other in 4-dimensional space, where the clusters sit. And so that's what the k-means clustering algorithm has attempted to do here. Now, I apologise for the colours. It's hard with this plot to get the colours to look up well. So if you can't see over the network, do have a look in the course notes on your own computer, and the colours might show up a bit better there. But the first thing to point out is that we've got 3 different colours. We've got a purpley colour, sort of a greenish colour, and a yellowish colour. And the other thing is that each of these panels is a projection of 2 of those dimensions against each other. So it's 4-dimensional data, but each of these scatter plots is a 2-dimensional projection of that data. So we end up with 6 different 2-dimensional projections of that 4-dimensional data. It's a little bit hard to think about multidimensional data. This is pretty much the best we can do. Looking at the purplish sample, we see that in almost all of the projections, that is well separated from the other cluster. So it's not surprising that k-means is able to easily pull apart that and draw a nice clear line separating it from the others. Now remember, when we were in 2 dimensions, we had a 2-dimensional, a 2-parameter line separating them. You can parameterize it with 2 variables, gradient and y-intercept effectively. Because we're here in 4 dimensions, we effectively have a 4-dimensional line separating each of our clusters. Hard to visualize, but imagine in 3 dimensions you would have spheres around each cluster. So in 4 dimensions we've got kind of 4-dimensional spheres or Voronoi cells. So the purple one is well separated, but as you can see in a lot of these, for example the first row, second column, you see that there the yellow and the blue points are actually overlapping with each other. Which might seem strange given that with our clustering we were seeing a nice strict line separating our 2 clusters. But the reason we're able to get information as to which cluster the green and the yellow belong to is because the clustering algorithm isn't working on each 2D projection individually, it's working on all of the 4-dimensional data all at once. And so it's managed to find a 4-dimensional line separating the yellow and the green, such that when you project it down, that projection line is kind of going up and down, but also slightly into the screen. And so it's separating the yellow and the green kind of above each other, if you think about if there were a 3rd dimension. And so even though in each of those projections there's not necessarily a clear separation, once you take into account all of the 6 projections, it starts being a much, much better way of separating your data. Also note that on the whole, thinking back to our correlation chapter, there isn't, in our correlation chapter we were saying that we wanted there to not be correlation between each of our features. We didn't want, for example, if we were doing a supervised model here, petal width and petal length to be correlated with each other. Now in clustering datasets, it's a different story. Because in a clustering dataset, you care less about the linear or scaling variation between the 2 of them. We don't care if petal width and petal length go up with each other necessarily. What we care about is how distinct they are clustered on the screen, not simply their covariance between the 2 of them. So it's a slightly more nuanced thing you need to think about with clustering compared to correlation with supervised learning, which again is why plotting on a graph like this is a really, really useful way of visualizing what your data is doing. So here we have our make blobs again. We've got our same centers before. We've got 500 samples, 4 centers, random state of 6. So it's going to be exactly the same data. As we loop through, trying out different numbers of clusters. So we're going to call k-means with n clusters equals 2, then 3, then 4, then 5, then 6, then 7. And for each of those times round, we are going to ask of the model how well it's feeling by the end. And the way you do that in scikit-learn is ask for the .inertia parameter. Now the inertia parameter basically relates to, by the time the algorithm has finished its job, how much were the points still jumping around? How much were the cluster centers still varying? i.e. how much inertia did they still have by the time it called it quits and said, I've finished clustering. So low inertias are good because that means that by the time the algorithm's finished, all the cluster centers had settled. A high inertia means that while the algorithm was running, those centers were jumping around a lot, and so it still hadn't found a good solution. So we want low inertias. We then take the inertia values for each of those numbers of clusters, and we plot a graph of one against the other. And this is getting to that elbow plot thing I was alluding to earlier. Number of clusters on the x-axis, so 2, 3, 4, 5, 6, 7 clusters. The inertia is, I don't know what units it's in, but lower numbers are a better fit. And so you see, by the time you've got to 7 clusters, it's managed to settle down quite well and work out where everything should be. However, we know there's 4 clusters, so we look at the value for 4 and we see, well, 4 got quite low as well. So the idea with these plots is you're supposed to be able to look sort of bottom left, see where it elbows and choose that as your number of clusters. But I've never ever been able to look at one of these plots and spot an obvious elbow. I wouldn't be able to pick between 3 and 4 on this unless I spent a lot more time doing this. So it's not always, to me, the most useful technique to decide how many clusters you should use. A more useful technique is to think about your data and think about the question you're asking, and see if that's going to give you useful information at the end of the day. That said, plotting an inertia curve over a couple of numbers of clusters is often a nice thing to do in case you spot any particularly interesting features. As I was alluding to before, and Al was asking when he was saying about logging your data and so on, there are limits to what k-means clustering can do. We saw, for example, that when you've got 2 blobs that are very close together, it's going to struggle to identify which cluster the points belong to. That somewhat is a fundamental restriction on what you can possibly expect a computer to guess from your data, but you can somewhat use some models if you know how the data is being generated to work out how you should cluster your data. So there are more advanced techniques you could apply. So k-means, which the clustering algorithm we're using here, is good because it's simple, fast, and easy to implement, but it famously has problems with clusters which are elongated. And so I'm going to switch now to a picture which is in the notes, so feel free to look at it there, which I've stolen from the scikit-learn documentation. So what we have here is a column for each different clustering algorithm. These are all fundamentally doing the same thing, just with different implementations. And each row here is a particular example of potentially tricky data, although I guess that row 5 is supposedly easy data. The k-means algorithm we've been using is that very first column there. So if you look at row 5, you see it's done the job just fine, like we saw. But looking at row 4, where we've got these elongated blobs, this is somewhere where k-means famously struggles. And that's because, as I was saying before, it always makes the assumption that the data you're working on is circularly distributed, or hyperspherically distributed if you're working in more dimensions. And that's because it always works by putting the center of the cluster in a place and working out the linear distance from there to any of the points. And that means if you've got 2 clusters which are next to each other and elongated, if you put the cluster in the center of one of them, then the points in the center of the other cluster are going to be nearer to that center than the points at the end of the elongated cluster that you've selected. And so it's going to do a bad job of working out which points each cluster should have in them. Looking across the row, we see there are other algorithms which do a better job because they do various other bits of transformation to your data. But there is other stuff we can do to our data first before we use k-means to kind of make it work a bit better. So one of them is dimensionality reduction. I mentioned principal component analysis earlier. One of the things that principal component analysis can do is take something that looks like the stuff on row 4 and turn it into the stuff that looks like row 5. And it does that by working out the principal components of the dataset, which would be along the length of the blob and across the width of the blob, and renormalizing the data so that it becomes more circular. Then you can apply k-means to your data set and you get it working. So by combining a dimensionality reduction like PCA with k-means, you can deal with a lot of messy data. That, however, isn't going to help with the stuff on the first row. The first row, PCA isn't going to give you anything directly useful because PCA tends to work with linear models. So here you can see that k-means has failed because while the outer and the inner ring are distinct, they share a center. They've got the same cluster center, and so it's not going to be able to distinguish which point each cluster should be in. So what you would normally do with this kind of data is look at it by hand and think about how you could transform the data mathematically to make it more easily clusterable. So one thing you could do with that first row, for example, is instead of plotting it in x1 and x2 axes, you could plot it in an r and theta axis. So you make some kind of radial symmetry. So you've got one, so you end up with two blobs, one at radius 1, one at radius 2, and the theta would then be all the way around, so you end up with two vertical blobs. That you could then cluster and get the right stuff working. In essence, that's what some of the other clustering algorithms that have worked here have done. They've done various transformations to the data implicitly in order to make the data more easily clusterable. So what I suggest you take away from this is A, if your data isn't going to work with k-means, either pre-process it with some kind of transformation, whether it's logging your data, making it radial, or using PCA, or consider using a different clustering algorithm and see which one works best for your data. So we're going to move on to the last section here, and that is using clustering for something which isn't just plain old data, but is something a little bit more visual. And so I'm going to open up a new console, new notebook. And we have 15 minutes left, and so I'm largely going to go through this and explain what I'm doing along the way. And I'm going to leave the exercise at the end probably as homework exercises for you. So we're going to start off by loading in a photograph. This is a photograph from Wikimedia Commons, and so it's openly licensed under Creative Commons. And we're on a new line, and we want to print out how big this picture is. So scikit-image is a sister project to scikit-learn, which deals with loading images. With io.imread, you can just load a JPEG from a URL, and you get access to it as an array on your computer. So let's have a look at this. It's a photograph which is 480 by 480 by 3. It is 3 at the end. It's a three-dimensional picture because we have a separate 480 by 480 matrix for red, for green, and for blue. So it's a cube of data, 480 by 480 by 3. And the fact that that's 3 is going to be important as we go through this. But let's have a look at what the picture actually looks like, because that's what we really care about. Show, another function from the scikit-image IO library, and let's plot the picture. And we get a rather nice picture of a swallow-tailed bee-eater bird. Again, I'm not an ornithologist, so I don't know any more about it than that, though I guess they probably eat bees. By default, the data in these images is ranging from, each value in the matrix is varying from 0 to 255. It's conventional to normally transform your data so that it goes between 0 and 1. Many machine learning algorithms just work a little bit nicer like that. You get normalized data, things end up just working a little bit better. So let's go ahead and scale our image by taking our data, loading it into an array. Oh, I need to import NumPy. Loading into array with a data type of float, and that's because when it was a 0 to 255, it was an integer. We want to convert it into a float so we can represent it between 0 and 1, and then we divide it by 255, and we're just going to overwrite the same variable. So it's the same picture, it's just all been made effectively much darker, but it's all got the same relative values. We then want to extract out the shape of our photo, because later on we're going to be changing the shape and we want to be able to reform the shape. So photo.shape returns the width, the height, and the depth of the image. That's 480, 480, and 3. We're going to save that in a tuple called original shape as well, and we're going to pull it out there. Once we've saved what the original shape of the image is, we are going to do something to it, where we are going to reshape it from being a 480 by 480 by 3 image, and we're going to change it so that the spatial dimensions just get thrown away. We are going to stop caring about where the pixels are, and we're just going to keep track of what the pixels are. So we turn it into something which has one dimension, which is width times height, which is going to be some number of thousands, and another dimension, which is the depth. And I'm going to save that as image array. And let's have a look at what that looks like. So here we see there is an array here, which has got red, green, and blue values between 0 and 1 for the first pixel, red, green, and blue values for the second pixel, red, green, and blue values for the third pixel, and so on until the red, green, and blue value for the last pixel down in the bottom right-hand corner. So this has effectively taken our picture here and has flattened it. So instead of being two-dimensional, it's just one long list of pixels, each of which has a red, a green, and a blue value. And that's because we're going to apply clustering on this, and we're not going to do spatial clustering in the sense of find out a pixel and then the pixels that are near it in XY space. We're instead going to find out the pixels that are near it in color space. So if we find a pixel that's yellow, we're going to try and find all the other pixels that are yellow. And we're going to try and make a yellow cluster and a green cluster and a blue cluster. And the reason we're going to do that is because if we can represent our bird with fewer number of colours, at the moment this bird is represented with 16 million colours or something. If we can represent it with fewer colours, one green, one blue, one yellow, while the picture becomes less nice looking, it also becomes much, much smaller in terms of memory usage. And so effectively what we're doing is creating a compression algorithm, something which can make our pictures smaller in memory, which means you can email them to people more easily and so on. And that's something we can do with clustering. We've got our image array here, but we want to stick it into a pandas data frame because then we've got column names and it will look something like this. A table with 230,000 rows because there are 230,000 pixels. Each pixel has got a red, a green, and a blue value. Once we've got those red, green, and blue values, we want to have a look and see how they're distributed. Now, red, green, and blue, you can plot it in one of two ways. You can plot it as a photo by using the red to change the amount of red on a pixel, the green the amount of green on a pixel, and the blue to change the amount of blue on a pixel. Or you could plot it as a cube with red on x-axis, green on the y-axis, and blue on the z-axis. And that will give you a sense of how the different pixels are distributed in colour space. And so we're hoping that all of the yellow pixels will be globbed together in one space in this cube, all the blue pixels will be globbed together in another place in this cube, and we'll be able to make that into a blue cluster and turn all the bluish pixels in the original image into that blue colour, therefore reducing the amount of different colours in the image, therefore reducing the memory usage. In order to plot this data, matplotlib doesn't understand 3 columns with different integers inside them, so we have to do a little bit of trickery, and I'm just going to copy and paste this. I'm not going to worry too much about how it works, but effectively it's creating a new column called colour, which has a hexadecimal representation of the colour made out of the red, green, and the blue values. So here we've got the red, the green, and the blue, and we've got a new column, which is colour, which has got 69 representing the amount of red, 64 representing the amount of green, 46 representing the amount of blue, and then 60 representing how transparent we want it to be. So this is RGBA hexadecimal code. The only reason we're doing this colour column here is for plotting purposes. This isn't going to be used as part of the clustering. We're just doing this to be able to draw a picture. Now, before we can draw a picture, we've currently got, what did I say there were, 230,000 pixels. That's way more than we need on our plot. So let's go ahead and take a subsample of our data randomly so that we've just got fewer pixels to worry about. So I'm going to take 5% of the data. So pixel sample is just taking a random subset of our pixels. So instead of having 230,000, we'll have 5% of 230,000. We can then go ahead and plot it. Feel free to have a look through this code later about what it does, but it passes in the samples, it tells us which columns we want to plot, and then it plots each of those pairs of columns against each other. So it's going to plot red against green, red against blue, and then green against blue. And so when we have a look at this, we get our scatter plot like we had for our iris example. So we have here on the first plot, red on the x-axis and green on the y-axis. So we were hoping that we were going to be seeing distinct red distinct blue blobs, yellow blobs, green blobs. But the most thing we're seeing is there's a big streak of sort of browny purple through the middle. And that's because the majority of the original image was background and the stick that the bird's on. So we're hoping that's not going to affect our stuff too much, but we'll have to see. But based on this three-dimensional data here, this no longer is a photograph. It no longer knows where the pixels go. It just knows how many of each pixel there are and what their values are. But because we've got some multi-dimensional data, we can just throw k-means at it and see what happens. So let's load in our k-means and then call k-means n clusters and underscore equals something. So at this point we want to choose how many colours we want to end up with. Now a photograph by default has got something like 16 million colours, 256 times 256 times 256, whatever that is. We want to reduce it down to something much, much smaller. For now, because my computer won't survive otherwise, I'm going to do 10. I ran this course last week, and when I tried to do 100, my laptop broke, so I'm not going to be doing that again. But we're going to try and cluster this data here with 10 different clusters and see what clusters it finds. And we fit it with our pixels subsample data, because we don't need all of our data. The 5% data is enough. And we're going to use the red, the green, and the blue columns. And we save that to a variable. Now this will take a little bit longer. It took maybe half a second. If I try with 100, my computer ran out of memory. Let's have a look and see which clusters it found. So we do that using k-means.clusterCenters, same as before. This is going to be a 3-column data set, which is going to be the red, the green, and the blue center for cluster 1, the red, the green, the blue center for cluster 2, the red, the green, the blue center for cluster 3, etc. But let's do a graph of it, because otherwise we won't be able to see it. In show, I'm using matplotlib here to draw a graph of that data. So you see here, these are the cluster centers that it's managed to find. Our original bird, I'll just scan back up to it for a moment, had yellow, green, and blue as its main feather colours, and the rest was kind of brown for the background. Our cluster centres from our data there has found a bluish one at the end. It's found a kind of muddy yellow in the middle, and it's found a grassy green at number 8 at the end. So it's kind of found some main colours, but you see the majority of it is brown. Using these found clusters, what we're going to do, we're going to replace, for each pixel, we're going to look up what the red-green value of that pixel is in the original image, work out which cluster centre it's nearest to, and replace it with the value of that cluster centre. And then we're going to plot that picture and see how it looks. So we do that by asking it for its labels, same as we did before. We are going to call the predict function. We're going to pass in all the pixels from our original image, and we're going to get back for each pixel in our original image the cluster center that the k-means algorithm reckons it's nearest to. And we've got a whole bunch of 5, 1, 1, etc, etc. There'll be numbers between 0 and 9. Once we've got that, we can go ahead and reshape it back to being square. So remember, our pixels was taken from being 480 by 480 by 3 to being some long list of numbers by 3. So we're going to put up our cluster centers back into the original shape and then have a look at what that looks like. So first we'll run reduced. And what I'm going to do is a plot of the original picture against our reduced picture. And you see here, it looks kind of ugly. But in terms of memory usage, this image is going to be thousands of times smaller to store on disk, and we're only using 10 different colors to do so. So what we can do with that, we can go up and we can have a look at how it looks if we change this to 15. I'm going to be cautious because I don't want my computer to break again. That 15 worked absolutely fine. And we run this and we're going to see that that picture on the right should become a bit better looking. Some yellows have started appearing, which they weren't showing up properly before. So as we increase this, we'll slowly get better and better representation, but we're going to get there a long time before we ever get to 16 million. This is actually often used as an artistic tool to make nice looking pictures if you choose your spatial orientation correctly. With the remaining few minutes, I'm just going to show you very quickly another technique that you can do to make your representation look a bit better. I'm going to change this back to 10. So I'm just going to copy this code in for demonstration purposes. So what we're doing here is we're going to take our red, green, blue scatter plot and we are going to perform a transformation on it by changing what's called the color space. So instead of representing each pixel in terms of how much red, green and blue it has, we're going to represent it by how light it is, which is what L stands for in lab, and how much of two other parameters it has. You can kind of think of this as doing a principal component analysis on it. We're then going to reorganize our data and look at what our new projection of 3D space looks like. So here we have the same data, but transformed mathematically into a different representation in 3D space. So instead of red, green, blue, we have L, A, and B. And you see here the clusters are much better distinguished. All that brown is no longer a streak through the middle, it's a blob. So hopefully that will be clustered more effectively. The yellow is distinct, the green is distinct, and the blue is distinct. So that means if we go ahead and ask it for a clustering of that data set, again using k-means fit of this new data, and have a look at what the clusters look like, we see we've now got slightly more variation in colour. We've got two different types of green and yellow and blue. Still got a lot of brown, but right now there's not a lot we can do about that. If we want to have a look at what our original bird transformed onto this clustered set looks like, we can do that. And here we see a different kind of reduction happening. With only 10 colours, it's got all of the main colours, two different greens, a blue and a yellow. But you see it's reduced the colours in other directions. Best way to see this is to plot all three of the pictures on one plot together. So here we have the original picture on the left, the RGB with 10 clusters in the middle, and the lab cluster with, again, 10 clusters on the right-hand side. Now, there might be pros or cons to one or the other, but certainly the one on the right-hand side has managed to pick out more of the interesting colours, whereas the one in the middle hasn't managed to find the yellow at all. So by choosing an appropriate transformation for your data, you can sometimes find more representative blobs, which are telling you interesting things about your data. For example, the middle one never found the yellow, whereas the lab cluster does manage to find the yellow. So we're basically at the end of the session now. So after the session, feel free to have another little scan through this page. There's some exercises at the bottom, which I'll leave for you to do for homework. So do have a go at those. And I'm just going to finish off with a bit of a summary as to what you might want to look into next. So this course has covered linear regression and clustering on the whole, but there's some other techniques which are really useful and can solve simple-ish problems but can be very powerful. One of those is naive Bayes, so it's worth having a read into that. That's a way of saying if the data was generated, how was it generated and what would the distribution look like. Support vector machines allow you to draw lines and separate your clusters of data, which is a really, really nice way of deciding how you should classify your data. Principal component analysis, I've mentioned. And neural networks, we have a course called Intro to Deep Learning, which we'll be running sometime in the future, so feel free to keep an eye out for that. And I'll finally point out some further reading you might want to look into. So the Python Data Science Handbook by Jake van der Plas is a really, really great book. It's free online. Do have a look at that. The Scikit-learn documentation's got lots of interesting pages describing how these techniques work. And if you're looking for a good book to talk through this stuff, right from the very basics through to advanced data analysis techniques, I very, very strongly recommend Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. I suggest you get the second edition if you can, which came out about a year ago. It's a really, really good book. It teaches almost everything you need to know about machine learning, data science, and data analysis. So do go ahead and grab that if you get a chance. With that, I'm just going to say thank you all very much for coming along the session today. We got through a lot of stuff, so I hope hopefully it hasn't been too quick, but it's been really great having you all along, and I hope to see you again in another course in the future. Thanks and goodbye.